Good evening, everybody. So, we have completed the part one, that is uniform flow, that we have completed. We have dealt in detail about the velocity, discharge, types of flow, types of channels, then conditions for most economical section, rectangular, trapezoidal, circular, and related problems. All that we have completed. Now we are transitioning to non-uniform flow. That is part 2. I divide part 2 into basically 3 questions. The non-uniform flow I divide into 3 questions. The first question is related to specific energy. The second question is related to gradually varied flow. And the last question is related to rapidly varied flow. And in today's lecture and the next lecture, 3 lectures I spend on specific energy, because this is the very important topic, not only for the semester end examinations, but also from the gate point of view. So that let us deal that. So today's lecture starts with the introduction of specific energy and then specific energy curve. And tomorrow, the next lecture, I take it to you application of this for a rectangular channel, understanding what is critical flow, what is subcritical flow, what is supercritical flow. Then once this is done, then we will go for problems. One class. So 3 classes we spend on this specific energy concepts. So that is what I want to tell you and take you into that. So let us straight away go into the specific energy concepts. So this lecture is mainly focused on the specific energy curve. These are the 2 things that I will take it. First, let me take what is specific energy. Suppose if I take this as a channel bottom, I'm taking it as a channel bottom. So this is the water surface, right? And this is the total energy line, right? And if I take a horizontal datum, this is datum. This is channel bottom. If I take the total energy from the top 2 thing, so this E part is V squared by 2G. This part is nothing but the water depth, that is Y. And this is nothing but the datum Z. So what is the now the total energy of the liquid per unit weight is given by number 1 Z plus Y plus V square by 2G. This is the total energy. So what is Z? Z is what we call it as datum head. Y is depth of flow, and V squared by 2G is nothing but the velocity head. So this summation is nothing but the total energy. For example, if you take, if channel bottom itself is considered as a datum, then the total energy per unit weight with respect to channel bottom is equal to, because this itself I am taking datum, the channel bottom itself we are considering as datum. Then above that, what is the energy? Actually, it is y plus v squared by 2g. This y plus v squared by 2g is called specific energy. So specific energy is equal to y plus v squared by 2g. How you define it? Specific energy. Specific energy of a flowing fluid, very, very important. Specific energy of a flowing fluid, right, is defined as the energy per unit weight of fluid. Here, fluid is nothing but water. Fluid measured with respect to channel bottom as datum. Please remember, the channel bottom itself is taken as, basically, this channel bottom itself is taken as data. So now what is the equation I mentioned? Specific energy equation is E is equal to y plus v squared by 2g. So in this, this represents, E represents, it is called as EP, and this represents EK. E is equal to EP plus EK. What is EP? What is EK? Sorry, EP. EP is the potential energy because it is head, the potential energy, and EK is the kinetic energy, right? So kindly remember. So if I take E is equal to y plus v squared by 2g, I can write it as y plus v square is equal to q square by a square into 2g. Right? Can I write like that? So q square by ag. Suppose, for example, if you are taking, if you are considering a rectangular channel, then what will happen? E is equal to y. Here it is q square. The bottom one is what a square is, b square y square into 2g. This also can be written as E is equal to y plus q square by small q square by 2gy square. What is small q? Small q is discharge per unit width. This is also one notation, nothing beyond that. And q is equal to q by b. Discharge per unit width. Discharge divided by width is equal to small q. So this q square by b square, I am writing it as small q square. Right? Now, so this is also equal to EP plus EK. So this is first introduction of what is specific energy. Now I am going for what is a specific energy curve. What is a specific energy curve? Specific energy curve is nothing but actually if you plot a graph between specific energy on x-axis and depth of flow y-axis for a given for this because this should be for a given discharge for a given discharge. That means discharge, it is a curve, it is a graph drawn between the specific energy and depth of flow for a given discharge. We already know E is equal to EP plus EK. If we plot separately, for example, then if you plot, for example, this is EP, right? And this is x-axis, horizon, y-axis. This is depth of flow y. Then you get a curve like this. It is a straight line here with 45 degrees. Similarly, if you draw a curve, horizon, x-axis is EK, y-axis is again basically it is only the depth of flow. Then if you get it like this. This represents EK, which is equal to Q square by 2G y square. And this is EP is equal to Y. So these are all true. Now, if I combine these two, combine these two, the specific energy curve is obtained. What I will write here, listen carefully. Suppose if I take horizon, x-axis, y-axis. On x-axis, we are taking specific energy. It is E. On y-axis, we are taking depth of flow, y. Right? What is constant? Actually, I already mentioned at the top, you write Q is equal to constant. Q is nothing but discharge. Discharge per unit width, that is constant. So now if we plot a graph, then how we are getting first thing is you draw a line 45 degrees line. This is first thing. Draw a 45 degrees line How the specific energy curve is plotted? Take actually on x-axis the specific energy, take the depth of flow on y-axis. Draw a basically a straight line at 45 degrees angle with x-axis. Now the specific energy curve will be, see how I am drawing it. This is how the specific energy curve is going to be. So this is point A, I call it as, end point is point B, and this point is point C. C. Now, if you see on this, basically how you are getting, you also, the specific energy curve has two limbs. What are the two limbs? AC is one limb and CB is another limb, right? The upper limb is AC, the lower limb is. These two limbs actually are asymptotic. For example, if you take AC, AC is asymptotic to 45 degrees line, whereas CB is asymptotic to the x-axis. This is the first sentence we should write. The specific energy curve has two limbs. First one, the limb AC is asymptotic to the 45 degrees line. The limb CB is asymptotic to the x-axis, right? And this OD, this is OD, call it as 45 degrees line. If you take actually at point C, the specific energy, if you observe, this is minimum, right? Corresponding to this minimum specific energy, this is called as, this depth is called as YC. An important point. So there is one point C where the specific energy, if you see minimum, you take any point on this specific energy curve, all points have specific energy more than at C. So that's why this is minimum specific energy. The depth of flow corresponding to minimum specific energy is called critical depth. This is important point. Now, apart from this, you take any point on the specific energy curve. If I take specific energy curve here, now if I draw a vertical, again it cuts the specific energy curve at this point also. At these 2 points, for example, if I call them as point 1, point 2, at these 2 points also, the specific energy remains the same. You observe it, take any point except C, you take any point on the specific energy curve, there for any point, for a given specific energy, there will be two depths of flow. If you observe it, this is one depth of flow horizontal. If you put it, this is one depth of flow, here also you put it. Suppose if I call this is y1 and if I call this as y2, both at y1 and y2, the specific energy remains as constant. This is the next point. The next point. If you observe actually, out of the two depths, one depth is less than critical depth and one depth is greater than critical depth. That is another point, right? So these are the points you should remember. Next point is, so the point corresponding to C, which is called as YC, relates to critical depth. Corresponding to this critical depth, the velocity is called as critical velocity. The flow is called as critical flow. And at critical flow, at critical depth or critical velocity or critical flow, the specific energy E is minimum. This is the first conclusion. Then second point is other than C, for any specific energy, there will be, I have shown already, two depths of flow, Y1, Y2. At Y1 and Y2, E is same. Y1 and Y2 are called alternate depths. What is the definition of alternate depths? The alternate depths are such that the specific energy is same at both the things. This is second point. The third point is out of the two alternate depths, one depth is less than critical depth and one depth is more than critical depth. If I take it, y1 is greater than yc. Am I right? If you see the drawing, therefore v1 is less than vc. The velocity at that depth is less than critical depth, and this flow is called as subcritical flow. Y1 is less than Yc. V1 is greater than Vc, corresponding to supercritical flow. And y is equal to Yc, V is equal to Vc. It is called as critical flow. So if you go back to the curve actually for you, or otherwise I will draw one more time the curve, no issues. Any number of times we can draw the curve. So this is, take it, horizon, x-axis, y-axis. On this is E, on this is Y. First thing is 45 degrees line. Then you take asymptotic to this, right? And again asymptotic to this. So this is the point where specific energy is minimum. Corresponding to this point is what we call it as YC. You take any other point, but that point there will be two depths. One is y1, the other one is y2. Y1 is greater than yc. Y1 is, for example, I mentioned actually, it is the y1 is greater than yc if y2 here. Y2 is less than yc. So now naturally, if I take here, basically, if I take the here, this 1 and 2 are called 1 and 2 are called alternate depths at both subpoints. The specific energy remains as same. Even I can call it as right. Then actually, if suppose I take here, so above critical region, this is all subcritical region. That's what I have shown. This is supercritical flow. At all the places where the depth of flow is less than critical depth, the velocity is more than critical velocity. That is supercritical. At all the places above critical depth, naturally the depth is more, the velocity is less, so therefore it is subcritical. Corresponding to C is critical flow. So the flow can be classified based on specific energy curve. One is supercritical flow, other one is subcritical flow, and central one, this line is, you can call rather than this line is better you put it. So this line, if I take it like this, subcritical, supercritical, corresponding to this is critical. So if you remember this diagram is for excellent question. Explain specific energy curve and its components, right? And then basically you put it this AC and basically ACB. This is asymptotic to the 45 degrees line. This is asymptotic to the x-axis, and already points I mentioned. If you mention that, that is more than sufficient. So I stop here, and in the next class, let us learn some more points on this specific energy. So in today's lecture, I explained you what is specific energy. Specific energy is the energy of flowing liquid, right? Per unit weight of liquid measured with respect to channel bottom as data. You know the total energy is Y plus V squared by 2G plus Z. If the Z is equal to 0 and the channel bottom itself becomes datum, the remaining two terms represent the specific energy. So specific energy is equal to E is equal to, it is denoted by capital G. E is equal to Y plus V squared by 2G. That is first. The second one is what is specific energy curve. Specific energy curve means you take a graph between specific energy on x-axis and depth of flow on y-axis. Then first draw a 45 degrees line. Then basically the specific energy curve will be such that it starts actually, it will be asymptotic to the 45 degrees line on one side, and it will be asymptotic to the x-axis on the other side. After drawing it, what are some of the characteristics? There is a one point where that one depth of flow is there, and that point the specific energy is minimum, and corresponding to that minimum specific energy, whatever depth of flow is there, that is called critical depth. So at critical depth, the specific energy is minimum. This you please put it. Then When the flow is critical, when the depth of flow is critical depth, the velocity of flow at that point is called critical velocity. Right. Forget about it. Next, you take any other point on the curve. For a given specific energy, there will be, you find two depths of flow. For these two depths of flow, the specific energy is constant. Such a depths of flow, such two depths of flows, they are called as alternate depths. At alternate depths, the specific energy is equal to constant. That is second point. Then third, these two alternate depths are such that one is above the critical depth and the other is below the critical depth. That third one. Then I told, if the depth of flow is greater than critical depth, right? If the depth of flow is greater than critical depth, velocity is less than critical velocity. All that region becomes subcritical flow. Whereas if the depth of flow is less than critical depth, the velocity is more than critical velocity, that region is a supercritical flow region. So the entire flow region based on specific energy curve can be divided into three regions. One is critical flow region, subcritical flow region, supercritical flow region. The depth corresponding to critical depth, minimum specific energy, the flow is critical flow. First point. Above the critical flow corresponding to that depth, that region is subcritical flow region. Below critical depth, that means there the velocity is more, that is supercritical flow region. So finally, what is the importance of specific energy curve is, it helps us actually to find out what is the how the flow is classified based on specific energy: critical flow, subcritical flow, supercritical flow. So this is what I covered today. I stop here. Thank you very much for your patience. Let us take the continue it in the next lecture. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.